Hello, everyone, and welcome to today's webinar. My name is Lisa Shaw, and I'm the Digital Specialist at SICK. SICK is one of the world's leading manufacturers of sensors and sensor solutions for industrial applications. Today, we are presenting Meeting Safety Standards with Autonomous and Collaborative Robots and Electronics Production, presented by Mark Nurkorn. With a little housekeeping before we begin, a recording of this training will be shared with you after today's presentation. Also, feel free to ask questions anytime by typing it into the Q&A section on the right-hand side of your screen. We will take some time at the end of the presentation to address as many questions as time allows. Now, without further ado, I will turn over my time to the presenter. Mark is the Director of Safety RCC Americas at SICK, holds a bachelor's degree in engineering management from DeVry, and has over 32 years of controls and automation experience, which makes him an excellent speaker to talk about today's topic. Mark, please take it away.
All right, well, thank you, Lisa. Good morning, everyone. Thank you for joining us today. The focus of today's presentation, to give you a quick overview of the current robotic safety standards that will provide guidance for the safe implementation of collaborative and autonomous mobile robots. This presentation roughly takes about 45 minutes, and we'll have some time at the end for the questions. Again, as Lisa mentioned, just go ahead and type those in during the presentation into the Q&A. So autonomous and collaborative robots support the implementation of autonomous production, electronics, and semiconductor industries. These types of industrial robots are perfectly suited for assembly and transportation of delicate products like printed circuit boards, modules, and finished goods. When we discuss industrial robots, traditionally, we typically think of these large industrial robots used in manufacturing. They're fast and powerful, very dangerous. Typically, we need to ensure the safe separation of affected persons in the areas, and the machine by space and time. However, new approaches, when we automate these types of things with new collaborative robots or collaborative robotics and human-robot collaboration, we want to talk about what does that look like when it comes to doing that safely. If you hear it's safe, you don't need any fences or devices, we should be very cautious because that may or may not be true. So hopefully by the end of today, we go through this information. Maybe it'll be a little more clear of how you should approach your application or your implementation of a robotic system. When we think about any safety application and the implementation of safety, we always talk about the 6 steps to a safe machine. So in this case, we're talking about the 6 steps to a safe collaborative robot or autonomous robot. And in any case, we always have to start with what are the laws, what are the regulations and standards that support those laws and regulations. So today we're going to actually take a look at quite a few standards and technical reports that are really supporting the laws. Typically, those standards give us guidance to perform a risk assessment. This is the first step. This is the understanding of the tasks and the hazards that will guide us through the rest of the risk reduction strategy. Once we know those tasks and hazards, then we can evaluate the risk reduction using the 3-step method of safe design, engineering controls, applying technical protective measures, and administrative measures that further handle other things left over, residual risk, things that we are going to apply typically on the user side of the application. Once a system is developed and designed and implemented into production, we're going to want to do an overall validation, the testing and the evaluation that we have met the intent of the risk assessment, and then either placing the machine into production as an OEM, maybe placing the machine on the market. And this way, we can be assured that we have met all the requirements set forth by the laws and regulations. So when we talk about laws and regulations, let's take a look at what the North American landscape looks like. So OSHA, right, is our legal requirements. The application of the law, the codified regulations, right, puts this onus of a safe robotic system or any safe machine operation is going to put this requirement or responsibility on the end user. So the requirement is that an employer provides a safe work environment for their employees, free from known hazards. So you may ask, well, how do I do that? When it comes to a robot, we then look to consensus standards. So consensus standards under ANSI, the American National Standards Institute, and the RIA, the Robotic Industry Association, who is the publisher of the standards we're going to look at today, will give the community guidance for how to do this properly. So these standards then support the application of the risk assessment, the risk reduction strategy and process for a robot cell or robot system, or a collaborative robot and robot system. So we'll take a look at these standards, these consensus standards, that will give the end user, OEM, or integrator the information necessary to meet those requirements set forth by OSHA. However, these are consensus standards, so they are voluntary. They're not regulatory required that you follow them. However, they are state of the art, and they will be referenced should there be an issue as a reactive approach from OSHA, potentially. So the standards we're going to look at, these third-party consensus standards, will be the ANSI RIA 1506. This is for industrial robots. We're going to look at a couple technical reports that are also published by the RIA that support collaborative robotics, and the technical report R15606 and technical report R15806 for testing methods for power and force limiting that is outlined in R15606. So let's take a look at the first standard and what it says about collaborative robots and collaborative robot systems. So first of all, how did we achieve the 2012 standard? How did we arrive at the 2012 standard for the RIA 1506? It was a national adoption of ISO 10218. So this is harmonized in Europe to meet the requirements under the machinery directive. So therefore, part one is industrial robots. So this part of the standard focuses on the OEM. These are the manufacturers of the robots and the robot controllers. Part two of the standard focuses on the integrator, the people building the robot systems, adding end effectors, tooling, and the workpiece, and ultimately the safeguarding required for a safe system, right? So the stakeholders for part two really are this end user, integrator to the end user, if you will, for the people who have to build the system. What we're missing in North America then, right, is all of the information that was in the previous version of the R1506 standard. That information was largely directed towards the end user. Because the machinery directive is geared towards the OEM or the integrator, this information doesn't reside in 10218. Therefore, this is the reason the RIA has supplemented the base standard, the R1506, with the technical reports that allows this guidance to be still remain to be used by the end user to provide a safe work environment for their employees. So real quick, let's take a look at some of the major highlights of the new standard, right? So we had to change some select terminology. No functional requirements, but we had to ensure that the terminology was meaningful. Definition of some of these new technologies and features, of course, we're going to talk about today when it comes to collaborative robotics. But certainly there were other new technology features like detachable wireless pendants, requirements for the safety-related parts of the control system. This is now functional safety, according to 13849 in the EU, according to the machinery directive. We also we had guidance now about safety rated soft axis and space limiting. This was a new feature. Came into being around 2007, 2008. The robot manufacturers started to implement safe axis limiting. Now the requirements for safe axis limiting were also added to the standard. Requirements for collaborative operation, as we're going to cover today, this was a new feature. So the new features of collaborative robotics was added to the base standard. And requirements for risk assessments. Risk assessments are no longer optional. It's a requirement of the machinery directive. Therefore, 10.2.18, as we've adopted, is a requirement that we now do risk assessments when implementing a safe robot system. The two technical reports we're going to look at for collaborative robots today as well, as I mentioned, these supplementary documents, right? Safety requirements for collaborative robots and testing methods for power and force limiting. Both of these are available. However, one thing we should remember, in the ISO, in a technical specification, the word shall is a requirement. It's a requirement in a technical specification, much like the base standard, where in North America, in ANSI, a technical report, we can only permit the word should. That doesn't carry the same weight, but when you read the word should in these technical reports, just remember this is a shall according to the standards we have adopted. Another technical report that gives guidance then to both the robot manufacturer, system integrator, and the end user is the R1506-306. This is a supplement that provides this guidance on performing a risk assessment. Remember, risk assessment is now no longer optional, it is now mandatory. So key elements of the risk assessment. So we're going to analyze the risk. We're going to evaluate the risk, and we're going to reduce the risk using the three-step method of safe design, applying technical protective measures, and then following up with any residual risk and other risk reduction handled by administrative measures. So this document then provides this guidance and asks the question of the tasks and the hazards performed by affected persons. If that risk is not appropriate or is not acceptable, then risk reduction measures in combination then with the supplier, the integrator, and the end user all can be used and implemented to reduce the risk. Whether the OEM design certain risk reduction features into the robot that is used by everyone when it's integrated and implemented into a system, and then very specific things that have to be addressed when tasks and hazards are implemented at the integrator level by an integrator or by a system designer, down to the end user, where tasks and hazards, cleaning, maintenance, and other things are carried on through the life cycle of the machine. It's always best to implement and think about risk reduction measures as the system is designed, developed, and built from the ground up. This way, you're more effective with your risk reduction. You can take into account all the things that need to get done in the proper way so that you can still build a safe and productive system. During your risk assessment, a couple of things we need to keep in mind. When we talk about human-robot collaboration, and certainly when it comes to collaborative robotics, people tend to think, the application, the robot is safe. It's safe right out of the box. I don't need anything else, right? It's safe by design. However, when you do a risk assessment, you'll quickly realize that as soon as I start to plan out whatever I'm going to do with the system I'm going to develop, you're going to have some end-of-arm tooling. Your end-of-arm tooling may create new hazards you haven't thought about. Here are some that you may want to think about, potentially. but in any case, doing a risk assessment allows for you to document the interaction with the end of arm tooling and what the realities of that is for the task hazard analysis set forth in the document for providing the work, the risk assessment. Like the end effector, we're also going to have to consider what is the actual function of the application. So now we have workpiece and or the process. We have to concern ourselves with the hazards associated with the implementation of the system. Therefore, these two factors, both the end of arm tooling and the workpiece of the process, typically is taken on by the integrator and or the end user. The manufacturer of the robot cannot typically understand what you're going to do with their robot. This will be on, this responsibility will fall to the integrator and to the machinery or system builder and end user. Once the risk assessment has been completed and one starts to think about the interaction of the human-robot collaboration, then if we look at the base standard, both in 10218 and or the R1506, and the new collaborative robot technical report or technical standard 1506 or the R15606, there are 4 methods that are covered for human-robot collaboration. So let's take a look at each one of these and take a look at what is required. So safety-rated monitored stop. This is a very typical interaction when humans have to interact with robots. If the person is in the area, there is no robot movement. It is in a safe stop position. The persons in the area collaborating or in the process area can be in that area at the same time as long as the robot is not moving. And the robot can be operating in that space as long as there are no people present in the area. This is allows for interaction with no motion. Hand guiding is permitted, but there are a few requirements for hand guiding. A safety-rated monitored stop is issued when the robot reaches this handover position. The operator will then have to guide and take over control of the end of arm tool and the workpiece with a specifically designed control device provided by the OEM that will allow for joint movement and positioning of the robot with limited speed and limited force. Once that task is done, this is then handed back over. The operator will release this mechanism, giving control of the robot back to the control system, ensuring that only during the hand guiding movement is allowed when the control device is in use. Speed and separation monitoring. So here, the dimension between a person approaching a moving robot is maintained through a sensor. The sensor then can slow the robot down, tell the robot controller, please slow the robot down. There is a person approaching. This minimum separation then between the human and the robot and its working is always maintained to be able to stop the motion when the person gets to the stopping point, so that there is no hazardous motion when the operator is within this dimension that is maintained by the sensor controller combination. Once the person leaves that safeguarded space and the sensor can send information to the robot controller that this has happened, the robot can then return to its normal operating speed. Last but not least, power and force limiting by designer control. This is a special feature designed into a collaborative robot. We will take a look at this here shortly, but power and force and ergonomic parameters need to be defined by the risk assessment. We need to understand where we expect potential interaction by the operator and the collaborative robot. Therefore, we can set these power and force limits correctly according to the guidance in the standard we're going to take a look at. So, as a supplement to the main base standard, R1506, the RIA has adopted the ISO Technical Specification 15066 and published it as RIA TR 15606. This is for collaborative robotics. So again, inherently safe robot. This is the idea that it implies that the robot is completely safe by design. Safety is on the inside. This is a very specifically designed robot, yes. It doesn't mean it's the only robot that can provide one of the four methods of collaboration. However, if you're going to do power and force limiting, then you will need a specifically designed robot, a collaborative robot that is designed. It contains hardware and software per ISO 10218, Part 1. So for the robot manufacturer, they include the safety-related part of the control system according to Performance Level D Category 3. And it maintains the safety-rated force and speed per ISO TS 15066, as I mentioned, which is also the adoption of 15606. So it is a very specifically designed robot. It's designed for direct interaction with a human when defined in this collaborative workspace. Now, the collaborative operation we've already looked at, there are four methods of collaboration, one of which is the collaboration with power and force limiting. So when this purposely designed collaborative robot wants to work in direct cooperation with the human in this defined space, we have that collaborative operation. If there isn't a direct connection, if there isn't a direct working with the robot in the collaborative workspace, then it's really one of the other aforementioned methods of human-robot collaboration. Could be coexistent, could be speed and separation monitoring, but it doesn't have to be power and force limiting. So within this collaborative workspace then, where we expect the robot and the human to share the space at the same time, performing tasks simultaneously during production operation, we now have this collaborative this operation inside the collaborative workspace. We typically want to take a look at this space, so when we set up a system or an application, we want to ensure that we restrict the operation of the robot, and we want to keep it out of areas that it is not expected to perform any activity. This way, the maximum space can be reduced. This special feature in the robot controller, this soft axis limiting, can be enabled to have the controller monitor the position of the robot at all times, knowing that it has boundaries and that it shouldn't exceed those boundaries. And then the actual operating space is a subset of that space, and we minimize then the exposure to other persons or other machine parts or other applications so that we can keep the footprint of our application as small as reasonably practical, right? This is then defining the collaborative workspace where we expect the human and the robot application or the interaction to take place. If we're going to implement these other collaborative applications, but are not using power and force limiting, then we may want to implement safe robot speed, where we are controlling the speed of the robot through a sensor and allowing full speed operation when there doesn't need to be any human-robot collaboration, but allowing that speed to be reduced and stopped and held position so that the operator may interact with the robot or the application and then have an automatic restart. We may have a safe robot stop where we have a coexistent application where we will use a more traditional stopping and starting of the robot. Again, not allowing direct human-robot collaboration when there is robot movement, but they can share a workspace potentially. And safe robot sequence, this allows for this speed and separation monitoring, but also will stop if your application is larger and has a different type of collaborative workspace and a restricted space. This is usually implemented in large or more complex robot systems or cells that are designed and developed. So these are other ways that we can also ensure the safety of the human-robot collaboration when not implementing power and force limiting. If you're going to implement power and force limiting, and you're going to set up a collaborative robot to operate with that method of collaboration, then you're going to need to take a look at ISO TS 15066, or in this case, we're covering this under the national adoption of the RIA 15, technical report, TR 15606. This is a national adoption of the ISO requirements for collaborative robotics. It includes important data from a study of pain threshold in Annex A, and this data then is used to set these power and force limits for expected interaction or contact with a collaborative robot and the human in the workspace. However, again, it still has the same structural issues from ISO to ANSI between a technical specification where the normative body of the standard includes the word shall and holds the same weight as the base standard, and in a technical report in ANSI where should, it's only recommended. We, when applying collaborative robotics, and specifically power and force limiting, we expect contact with the robot and a human. Therefore, we needed to set these limits, or the standard needed to set some limits or guidance for the end user of how to set these power and force limitations so that people are still afforded a safe operation when coming in contact with the robot. So we have acceptable areas of this force, both for quasi-static and transient type of impacts with a robot. So the study was conducted. This was a research project taken on at the University of Mainz by the DGUV, which is the German Social Accident Insurance Association. They founded this test and built a machine to prod and poke different parts of the human body until the onset of pain threshold was noted by the test subjects. They tested 100 different people and then created all of the information that is in the annex. So this gives guidance then to the end user when the risk assessment says, I expect that potentially there will be contact between the end effector or the tool used in the operation in an operator's hand, then I know the kind of force that is permitted under the guidance of the standard to be exerted on the back of the hand or the arm or the leg or the abdomen. And this, therefore, is used to set the limits of the robot according to the risk assessment. One thing that is not acceptable, however, is any contact with the skull, the forehead, or the face. So this is something you have to keep in mind when you do a risk assessment, that if you expect to have some sort of interaction and this is a potential contact area, you should really reduce or eliminate this as far as practical and look for other ways of ensuring that we don't have contact with the skull, forehead, or face of the operator and the collaborative robot. This is not something we want to have happen. If you're going to implement power and force limiting within the collaborative robotics guidance found in the standard, one of the things that we need to do is ensure the validity of those settings, right? Robot manufacturer builds a robot, and they, again, don't have the information that the integrator or the end user has about the tooling, the workpiece, and the application. Therefore, they can give you the ability to set the forces and the limits and speed but that is going to have to be adjusted according to this process or to your end tool effector mass and speed that you're going to accelerate that mass of the end tool and the workpiece. Therefore, this needs to be validated. So you will need to do testing and measuring to ensure that you are not exceeding those values in reality with the impact of the system and or the transient impact, both the force and the impact. So this validation needs to ensure that the speed is set correctly, that the working area is restricted correctly, and that the overall forces exerted on different parts of the body according to the risk assessment have been verified and validated that they were within the ranges set in the controller. We do that with a testing method that is outlined for in the R15806 technical specification. This gives us guidance on how to take these measurements and how to validate that your power and force limiting is configured properly for your application. So quite often, this is an integrator end user type of responsibility. Let's move on to industrial mobile robots. So the RIA has also taken on a new work item. This is the RIA R15.08. This is under development. This is a new standard for collaborative and autonomous mobile robots. So currently, there is an international truck standard for AGVs. This standard supports autonomous guided vehicles. So these are guided vehicles under B56.5. And ANSI, as we just looked, has a North American robot standard for the R1506. But what we don't have is the combination of these types of vehicles and or combination of vehicles and articulated accessories or attachments that have autonomy. Therefore, the RIA has taken on a new development for a standard that will cover these autonomous mobile robots. So part one, much like the R1506, will be for the suppliers of these devices. So this is under development currently. The integrators then in part two, again, will be covered for the implementation of a system or a autonomous mobile robot cell and or system by an integrator or an end user. And then certainly part three, for end users, more detailed information for the end users. As we can see, autonomy brings in quite a few other things we need to think about with navigation, AI, mobile robotics, how the transportation mechanism is implemented in the platform, if the platform is stationary but we have attachment movement. So what may be attached? We have autonomy, so it has some ability to do its own navigation, find its own route through the plant or the facility. And if there is a robot attached or other attachment to the top of a mobile platform. All of these have their own issues to deal with when it comes to safety. So let's take a look at the current scope of the work going on in the standard. So it will be industrial. The standard will be for industrial use. So therefore, there will be no guidance for public spaces. So these devices developed to be used in a public space, the standard is not going to be utilized for that. This is an industrial standard in an industrial environment where we assume that there is some commercial relationship between the affected people and the owner of this establishment. So therefore, they can be trained to understand how to implement and use and work safely around a mobile robot or mobile robot system. So mobile does refer to ground-based. So this will not include airborne or waterborne systems or mounted on rails. These will be out of the scope of the standard. If we're going to go outside, however, with this mobile robot system any environmental impacts or environment needs to be considered by both the manufacturer and the implementer or integrator, so that we're using the right system and it is implemented properly in a safe way under the conditions that they expect and the limits of those conditions as set forth in their design specification for the intended use. So there's three basic constructs of what we're calling a robot under the standard. It applies to both industrial robot manipulator attached to a mobile base, which may or may not be fully autonomous in its own right, a mobile base that possesses a degree of autonomy greater than that of a traditional AGV, even if a robotic arm is not attached to the base. So this would be a mobile platform. And then a single unit designed to have the capabilities of both a mobile base and a robotic arm, and a degree of autonomy capable of operating in a dynamic environment. So what does that look like with the current standards we have, and how do we sort through what we have? So if we have a manipulator, we have a multi-axis manipulator greater than 3 axes, we already have a standard that we just discussed. This is the North American Robot Standard. This is the R1506. So robots are still covered under that standard. If we have an AGV, what's considered an AGV, right? We have an automated guided vehicle. It does not have an attachment. Then it is covered under the current B56.5 standard. However, if we have a mobile platform and it has no attachment, this standard will support that in a type A. This will be called a type A mobile platform under our AMR, under this standard under development. If we have an attachment to that platform and it is not a 3 or more axis manipulator, then this will be a type B AMR with an attachment. If we add this articulated arm to the top of that mobile platform, now we have a type C mobile manipulator. So these are the 3 types of AMRs that will be covered under the standard. However, if we have an AGV and we're going to add a manipulator, i.e. an articulated robot, to the top of an AGV, there will be guidance in this standard also under the type C mobile manipulator. So wrapping up the webinar today, SICK supports the realization of all of the complete safety solutions that provide safe work environments, safe production environments and applications, from risk assessment through the validation process for all of our strategic customers in these types of applications in electronics, assembly, and transportation and logistics through final goods. We can support robot users, manufacturers, OEMs through the realization of the safety services that can be provided to do the safety consulting, Safe Robot. We have over 70 specialists worldwide and 100 certified safety specialists worldwide in over in 80 countries worldwide with 88 office locations to provide a complete safety consulting and solution support. With that, is there any questions?
Cool. Thank you, Mark. Yes, we'll go ahead and open for any questions. Just a reminder, if you have any, please type them into the Q&A section in your control panel, and we will answer as many as we can.
All right. So let's take the first question. Is a collaborative, purposely designed robot necessarily to fill a collaborative application? And the answer to that is no. As we discussed, there are 4 methods of collaborative applications, of which only one, power and force limiting, requires that purposely designed robot. This is what people refer to as a cobot, a collaborative robot. Next question. Is safety, risk reduction required for a collaborative application? Yes. The inherently designed, this inherently safely designed robot we call a collaborative robot still has risk reduction in the power and force limiting and the speed limitations that are inside the controller. That is still a risk reduction strategy. It may be that your application, that is enough. But through your risk assessment, you will have to define what is the application, how much power, i.e. how much force and speed do I need for my application, and according to the chart in the annex of the TR 15606, can I live with that potential interaction with the human and the robot then under those power and force limiting restrictions? If the answer is no, then you may need some supplemental risk reduction. If the answer is yes, I can maintain those power and force limit exposures in that application, then maybe the risk reduction in the power and force limiting in the controller is all you'll need. As always, risk assessment will define what risk reduction is going to be necessary. Okay. Next question. Is a defined collaborative space required to implement a collaborative robot application? Yes, you do need to define through the risk assessment and in your application where the human-robot collaboration or this coexistent interaction between the robot or collaborative robot and a human will take place. And where that takes place is the collaborative workspace. Within that space is where the risk reduction of either power and force limiting or speed separation monitoring and or hand guiding will have to take place. Okay. If there isn't any other questions, then that wraps up today's webinar, and I want to thank everyone for joining us today.
Thank you, Mark.